So let's have a look at the graph of the basic trig functions. So our sine curve, you'll recall, has an amplitude of 1. So we'll plot that in. Now I'm going to mark off the x-axis, but we're going to use radians this time instead of degrees. And I might have got a bit carried away there. I've gone all the way up to 4 pi and back to minus 2 pi. Our sine curve, of course, starts at the origin, and then we go up to the amplitude, and then basically we zigzag all the way along, backwards and forwards. But of course we don't draw in a zigzag, we draw in a nice smooth curve. So there's sine x. So what can we see? We know it's domain, or real x, range minus 1 to 1. We can see that it's an odd function because it's got the rotational symmetry. So that means we could use this property. The sine of negative x would always equal the negative sine of x. Satisfies the rule for an odd function. The period of a trig curve is how long it takes for it to repeat. But when I say repeat, it has to be identical. So for example, if we were to look at the x-axis here, it's tempting to say the period's pi because we're back at 0. But at 0 it's going up, and at pi it's going down, so it hasn't repeated yet. It's got to be going in the same direction. So for that reason, it's 2 pi. Any point you like will be 2 pi. So our period is 2 pi. The amplitude is how far from the axis. Let's have a look at cosine. And basically it's the same graph, of course, because cosine means complement of sine. Let's plot in cosine. We would start at the amplitude, of course, for cosine, then come down and, there we go, zigzagging along, backwards and forwards, drawing the curve. But of course it is the sine curve shifted by pi on 2. Hence complementary. So because they are complementary curves, we should see the same things happening. Domain is all real x, range is still minus 1 to 1, that doesn't change. But this time we have an even function rather than an odd function. So we could say cos of negative x is equal to the cosine of x. Period is still 2 pi, amplitude is still 1. So cosine, yes, it's the complement of sine, so hence we have the sine curve shifted 90 degrees. Although technically it's more than a shift because it's negative x. So technically what we've done with the sine is we've reflected it in the y-axis and then shifted it 90 degrees to the right. Alright, let's have a look at tan. Tan, I'm marking off my axes again. Notice I haven't bothered marking anything on the y-axis. There's not much point. I mean, a tan curve doesn't have an amplitude. But our pattern here is, we know we start at 0, but then we have an asymptote. And then that pattern repeats. And we bend towards our asymptote. Make sure when you're drawing your tan curve, it goes through at 45 degrees. So don't draw it like a cubic, which some people are tempted to do. It comes through at 45 degrees. And that repeats between each asymptote. So let's have a look. Now this is a little bit more fun trying to write the domain for this one. It's all real x, except, well, I've gone with pi on 2, because there it is at 90 degrees, but then of course every pi before and after that, we find another asymptote. So I've just written that as well, plus pi k, where k is some integer. The range is all real y. In this case, it's an odd function. We've got our rotational symmetry. So tan negative x is negative tan x. The period for this one, of course, is just pi, not 2 pi. Let's do cosecant. Cosecant is the reciprocal of sine. So if I just draw in the basic sine curve, and now we're going to draw a reciprocal curve. Now we remember our rules for reciprocals. X-intercepts become, right, so all of those x-intercepts are now asymptotes. Now when we turn 1 upside down, we get 1. So all of those peaks of the curve, they're going to stay at 1. But the other thing we said was anything below 1 will go above 1. And anything above 1 will go below 1. And another way of thinking about it with curves is when it's concave down, it'll go concave up and vice versa. So what we end up with is a series of, well, they're not parabolas, but a series of U-shapes between our asymptotes. So there's cosec. All right. 11J.